Hello, this is Mr. Jackson and welcome to Chemistry A again. Today we're going to continue on our discussion in Unit 2 of the atom. Remember we talked about last time all the famous chemists who had helped us develop a picture in our mind of how the atom may look inside using indirect evidence in some of their experiments. And we came along and we finally got down to our last two ideas, which was the Bohr model and the wave model. But we know that the wave model is not very good for teaching, so we're going to be using this Bohr model more often. And so we'll get to that today and talk about how to draw a Bohr model at the end of this discussion. So let's move on. Today I want to talk about the basics of what is in an atom. And we know what those particles are, but let's talk about those particles that are inside. Okay, so first of all, number 9, we ask us what is an atom and what properties do they have? An atom is the smallest part of any element that contains its properties. So a hydrogen atom has a specific amounts of electrons and protons and neutrons that are identified as hydrogen. And then you might have oxygen, which has a different amount of electrons, protons, and neutrons, which makes it an oxygen. So those groupings of particles give it its properties, and each element has its own unique properties based on its amount of particles that it has. Okay, so once you have an atom is the smallest part you can have of a particular element that still retains its identity. Okay, so first of all, let's talk about what's in our nucleus. We know that there's an inner center part that has got some particles in it. Those two particles are protons and neutrons, okay? And they do have a weight, and their weights are extremely small. In fact, that's posted in our book, and the proton has a mass of 1.67 times 10 to the negative 24th grams. That means to write it out without a power of 10, I would have to take this decimal place and move it 24 times to the left, which is an extremely small number. It's extremely light. And so rather than writing these kind of numbers down, scientists have called this amount 1 AMU, an atomic mass unit. Okay? We've also discovered that a neutron has the exact same weight. So it also has a mass of 1 AMU. So we're going to be using these numbers and not their original gram weight. Okay? Now, each particle, as our scientists discovered, as they're trying to figure out the atom, they discovered that the proton actually has a positive charge, which was deflecting the alpha particles in Rutherford's gold foil experiment. The neutrons have no charge or are considered neutral, which the name neutrons came from. So we have usually giving them a 0 charge. Okay? So those are the two first main particles that we find inside the atom, but actually located in the heavy, dense center called the nucleus. Okay? And one thing else we've discovered is that basically about 99.999% of the mass of the atom is found in its nucleus. So most of the mass basically is found in the dense center, so we are discovering that basically the atom is mostly empty space. Just the heavy particle, and then the heavy dense particle called the nucleus, and then the other particles around the nucleus, which we're going to talk about. So how do we determine what is in a nucleus from the periodic table? So I'm going to do a quick overview of a periodic table. We're going to go deeper into that in the next few days. But I want to talk about the numbers that we find on a periodic table. On a periodic table, there are symbols that usually come from its name. It's not always true because there are other names like iron, but it has a symbol Fe from its old Latin name ferrum. So some symbols don't match their now current today's modern name. But they do have a symbol, either one capital letter or 2 letters, but the second one will always be smaller case. Okay? And if they have 3, it means they've been submitted to the Chemical Society, but they haven't been accepted yet as being real elements. So the majority, once these become accepted, they will be giving a 2-letter designation. Okay? And so we have all kinds of that. In the box, we also have a number, which is called the atomic number. The atomic number is actually the number of protons within that element. So that means that lithium over here has 3 protons in all of its atoms. Boron has 5. Nickel has 28 protons in all of its atoms. If it doesn't have 28 protons, it is not nickel. That's its identifying mark. Okay? So the proton number is defined as its atomic number. But then in each box, there's an atomic mass. And the atomic mass is this mass of the nucleus. But that means that this number right down here, these decimal numbers, like this one right here of 58.893 for nickel, that is a blend of all the possible type of nickel atoms that can have a little bit more weight or less weight by having different numbers of neutrons. And so this weight, or this number down here, is the number of the mass of all the protons and neutrons together. So it is equal to protons and neutrons. Okay? So if we really wanted to find the number of neutrons, what we would do is we would take that atomic mass, we would round it off to a whole number, and then subtract the protons, and then we could discover how many neutrons are in that particular element. So let's just do a quick example. Let's say that we have lithium, okay, and lithium's mass right here is listed as 6.94. And so if it's 6.94, and I'll zero in here so you can see that, we have 6.941, so that's close to 7, but it has 3 protons, so 7 minus 3, and so that gives me 4, so that means this lithium has 4, most commonly, neutrons in its nucleus. So by subtracting these two numbers, you can get the neutrons, okay? And that's how you would do that, but you have to round this number right here to the nearest whole number. Like beryllium is 9.012, so 9 is its most common state. So 9 minus 4 is 5. It would have 5 neutrons in that beryllium atom. Okay? That's how you would figure out the neutrons. Now, there are also, we've been talking about our model up here with the wave model, and we know about these rings up here, that these are our electrons, the negatively charged particles. They are also found in the atom, and they're surrounded in the area called the electron cloud. Okay, so a lot of times this is in the area called the electron cloud, and they circle around at the speed of light, which we talked about earlier, moving from area to area, staying within a ring of energy. So they may pop in and out here, then over there, and there, but they'll stay within their distance or their ring energy amount, okay, as they move around. So let's describe their charge and their mass. They have a negative charge, and their mass is considered to be insignificant or negligible. What do I mean by that? Is if you look at all the weights, the electron is 10 to the negative 28th instead of 24, so that would be 0.0001 AMUs, which means it'd be like trying to weigh your body and then putting a dime in your pocket and then seeing if it changes the weight on the scale. And it really doesn't. So the electrons are there, but they contribute so little that they pretty much all the time give them a value of 0 AMU because it's so small or insignificant. Okay? So that's the mass and the charge on the electrons. Electrons move very fast all the time, and they can leave the atom under certain conditions, but we'll talk about that more often at different times because we send electrons down through wires, so we can shift them around. They're actually pretty easy to take off of an atom and shift from atom to atoms and do all kinds of stuff, but we'll talk about that. It's a very important topic, and we will get to that. Okay, but the electrons, as they stay around the atom, they always stay in a particular energy level. Okay, and how many can we fit in these levels? Well, we know that there are lots and lots of levels available around every atom. Okay, they may not use all the levels, but they're available. So let's talk about those levels. Those levels, there are numerous. Let's just talk about the first 4. The first 4 levels have a certain amount of electrons they can hold. The first level can only hold 2 electrons, and that's because that level is so close to the nucleus. So here's our nucleus. The level is so small, and at the speed of light, it can only fit at the most 2 electrons. Okay? But then if you want to go to the next level, since it's farther away in energy and it pushes it farther away, then there's an ability to put up to 8 different electrons if it's full. It doesn't mean it has to have 8, but that's the most it can hold. Then, of course, as you go to the third level, it can also hold 8. And then the fourth level can hold 18. As you get farther and farther out, you can keep holding more and more and more electrons. But we don't need to memorize this. This is on the periodic table. And I'll show you how to figure out the number of electrons. On a periodic table, this was carefully designed by scientists. This is the first ring of the atom. It has 2 boxes, so it can only hold 2 electrons. The next energy ring is right here, which is the next row in the periodic table, and it has 1, 2, 3, 4, 5, 6, 7, 8. So the second ring can only hold 8 electrons. Then the third row right here is the third ring in our Bohr diagram, and it can hold 8 electrons. And then as you go to the fourth row, then this block right here kicks in, which is 10 boxes long. So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So the fourth row can hold 18. And of course, as it gets bigger and bigger and bigger, we can hold more and more electrons, okay? And so you don't need to memorize. You just have to be able to look at the periodic table, and it's quick and easy to figure out. Okay? So let's keep going on. We're almost done here. And we can talk about our next ideas. And here are our next ideas. Let's summarize what we've learned about the atom particles. And here's what we've learned. We have learned that the electron, which usually is given as symbol E-, has a negative charge. It has a 0 mass because it's so much lighter than the rest, and it's found outside the nucleus in the area called the electron cloud. The protons, which are usually giving a P with a plus charge, they have a positive charge, they have a mass of 1, and they are found in the nucleus. And then we've talked about the neutrons, which basically all they do is add mass to the atom, and so they have no charge at all, so they're neutral. They have no charge. They have a mass the same as a proton, and they are also found in the nucleus. Okay? So these are the main particles we want to talk about in our level, this level of chemistry, okay? So I wanted to summarize that for us. These are the most common symbols you'll see in your text in your book when you read. Okay? So let's finish up here really quick. We talked about that the mass of the electron is negligible, so we call it 0. I added that into our notes. It's important. So how can we determine how many electrons there are in an atom from the periodic table? Because if we go back to our periodic table, we realize that we have these big numbers, which are the number of protons, and then we have these atomic masses, which are decimal numbers, and they are an average of the protons and electrons, but we don't have no electron numbers. Well, in the most common state, almost all matter that we touch is neutral, which means the protons and electrons are equal. So neutral atoms have the same number as the protons. So a neutral sodium, since it has 11 protons, it will also have 11 electrons. So in a sense, the electron number is given to us, but we'll talk about when that can change. So for right now, in a neutral atom, there are equal amounts of protons and electrons. Okay? Because in a neutral atom there is no charge, okay? And so that means they're balanced. So how can we simplify a nucleus for big atoms when we're doing a large Bohr diagram? Well, let's talk about that, and let's show you the easiest way to do a Bohr diagram. So I want to take about a minute here before we finish and do a Bohr diagram with you. Let's say that we have lithium, and I want to draw the Bohr diagram for lithium. So how would I do that? So here we go. We're going to do this. We got to first of all look up lithium's numbers. Lithium has the atomic number 3, and its mass of 6.94 rounds to the closest whole number of 7. So it's got 3 protons, okay, and its neutrons, it's going to be 7, which is its mass rounded up, 6.9 rounded to 7, minus 3 is 4, so it has 4 neutrons. And so what I'm going to do, rather than drawing 3 circles for protons and 4 circles for neutrons. I want to keep my thing within this box, my Bohr diagram. I'm just going to go 3 protons, or just put 3 plus, that's fine too. And I'm going to put 4 neutrons, okay? And then I'll just draw my rings. Well, how many rings do I need? Well, that's really simple. I have lithium, and it is on the second row, so I need to draw 2 rings. So 1, 2. Okay? And so we draw on our 2 rings, okay? And so now we want to figure out how to put the electrons in. Well, remember, you always put electrons closest to the nucleus first before you go outward. And to get to lithium, I have to go through boxes 1 and 2. So in the first row, I'll put 2 electrons. Okay? And then we know we have 3 protons, so I must have 3 electrons. And so I'll put the last electron out there in the outer shell somewhere. Okay? So that would be my Bohr diagram for lithium. Okay? Why don't you go ahead right now and pause this video and try to do the oxygen one, okay? Okay, if you're going on, now let's do our oxygen. We'll look up our information. My oxygen has 8 protons. So I know I have 8 protons. Now I want to figure out the number of neutrons. I look at its mass. It's 15.99, which is close to exactly to 16. So I'm going to round to 16. 16 minus 8 is 8 neutrons. So now I've got the nucleus. Okay. Now I want to figure out how many electrons and how many rings. Well, it's got 1, 2 rings. Okay. And it's going to have 8 electrons in those rings. But the first ring will be full with 2, and then the rest will go in the next ring. So I'm going to draw 2 rings, give it 2 electrons, and you could put a dot or an E, and then I'm going to draw a second ring, and I'm going to add the next leftover ones, and I've already given it 2, but I've got 6 more to go. So 1, 2, 3, 4, 5, 6. Okay? And that would be the Bohr diagram for oxygen. Real simple. Okay? So I just wanted to show you how to do those today, and that's a quick overview of our atom basic particles. Thank you for joining me. I appreciate it.